Next speaker, Professor Louis Rowen from Bar Ilan University. Professor Louis Rowen will have a talk, linear algebra of algebraic pairs.
Oh, thank you very much. It's really a pleasure to be able to talk at this conference. We're just trying to work out the, this is an attempt to make this mathematical model which includes tropical geometry. So a rather general mathematical model. And so let me just start with a brief review of tropicalization. So tropicalization was a very successful tool of studying real affine geometry by taking the logarithms of the coefficients and then let the base of the logarithms approach zero. And in such a situation, certainly the multiplication becomes addition, and the addition at the limiting case becomes the maximum. So this leads one to the max plus algebra, and which is very well known, very important tool. But the problem is that you can't take the logarithms of complex numbers so easily. You can take the absolute value. So an alternative to the max plus algebra was, or an alternative to the log map was investigated, and oh, this isn't working. I need to have
just okay. One second. גרסה קודמת, אבל זה יעבוד כמו שצריך.
בסדר.
אתה צריך לעשות שם אחרי.
I'm sorry, we're having a technical problem here. Wait, it might work this way. Okay. Wow. No,
Just a second.
well, I'll go through it this way.
Okay. Oh,
Okay,
fine.
Great. Okay, so I'm terribly sorry for the interruption. So the alternative was to use the Puiseux series, which is almost like a power series ring. The specific definition is given here, and this has a valuation, namely the leading term, or negative, the minimum term, and which is it? Okay, so so this was the substitute for the max plus algebra. Now, one can observe that the target, which is an ordered semigroup, can be viewed as a semi-ring simply by defining the plus a plus b equals b if and only if a is less than or equal to b. And this is sort of a bipotent semi-ring. A plus b is either a or b. And so evaluation of field is a map of semi-rings. Now, the advantage of the Puster series is that the Puster series algebra over a algebraically closed field is also algebraically closed, and so is elementary equivalent to C. So by using this valuation, one could bypass the problems of logarithms and go directly to C. And the only problem is that the valuation is not a homomorphism. The valuation, of course, is the maximum when valuation of F is not equal to G, valuation of G. But of course, when the valuation of F is equal to the valuation of G, then you lose the leading term at times. So we needed a substitution for viewing the valuation as a homomorphism of semirings. And this was handled by Itzakian in his thesis with supertropical algebra, where he had two copies of the structure, two isomorphic copies, and he took the sum to be the maximum when their values aren't the same. But then you move from the first copy to the second copy when the valuations are the same. Let's see if here A naught is the value of A. Okay, so that's addition, and multiplication is just usual multiplication, except that for the first component, for A, B, and T, A, B is just this product. But when one of them is in the second component, the product is automatically taken in the second component. So in other words, G is a semi-ring ideal of A. Now, okay, the characteristic 1, 2 means that 1 plus 1 is one circle, and one circle plus 1 remains one circle. So after you get to one circle, you stay in the same place. And so that's different from the normal maths plus algebra, which is characteristic 1, 1. So now researchers were trying to find how to handle this in semi-ring theory. And one important notion, which we'll deal with soon, is actually dates back to Marty in 1934 and Krasner in 1935. It's a hyper semigroup. Instead of the addition being in H, the addition is in the power set of H, or the non-empty sets in the power set of H. And then you define addition component-wise in the power set. And 0, called the hyperzero, is the neutral element. 0 plus any element of A, any element A is the set A, singleton A. Okay, so a hypergroup, so that was a hypersemigroup. A hypergroup is a hypersemigroup in which every element has a unique hypernegative, which means that 0 is an A box plus minus A. And so this is in the power set, and the sum has to include 0 as an element. So when H is also a monoid, then you have a element-wise multiplication, and that altogether makes the power set a semi-ring. It's almost a semi-ring, but sometimes one doesn't get distributivity in the power set. So that's a bit of a pain, but one often has to deal with the lack of distributivity. Now, a hypergroup H will be called a hypersemi-ring if this multiplication is distributive. And a hyperring is a hyperfield if this is a multiplicative group. Okay, so Vero showed that the supertropical algebra of Yitzakian can be viewed as a hyperring when we define the set addition of A and B to be all C, which is less than or equal to A plus B. So supertropical algebras fit into the hyperring construction. Now Krasner has a very beautiful construction, which dates way back into the last century. So if you have any semigroup and you have a map onto another set, then you define the hyper addition to be the set of all elements whose pre-image, the pre-image of the sum of A plus A prime, or A bar plus A prime bar. And if S is a group, then this is a hypergroup. And if you start with a monoid, then you can get a hyperaddition in this way. Suppose you have a monoid and a subgroup of the monoid, a multiplet, I'm sorry. If you have a semi-ring and a subgroup of T0, where T0 is contained in R, then you can take the cosets of the ring, modulo this semigroup, and you define the hyperaddition by, again, you take the sum of the cosets to be the coset of the pre-image of the sums, and the multiplication is the image of the multiplication, modulo G, and that will give you a hyperring. And if R is a field, you have a hyperfield. And as I said, you can do this for semi-rings also. Okay, so this is a very important construction. And now some general background. Lawshield developed a system of blueprints to provide an algebraic setting for tropical algebra. And we introduced triples and systems, which somewhat generalize that. But what triples do is they provide a formal negation map, which is not the real negation, because A minus A doesn't have to be 0. So all of the elements of A minus A is a set which replaces the 0 set. And so this was a way of handling semi-rings without having negatives. And my point today is to further generalize this to the notion of a pair. For 4:30. A pair where A is a semi-ring and A naught is a distinguished set, and you can do it without distributivity. Okay. So the morphisms, which we call weak morphisms, are functions that don't necessarily preserve addition, but they preserve this property, that the sum is an A0, then the sum of the images are in A0 prime. We can call these the null elements. Sorry. And you have two possibilities. The tropical possibility is A plus A is always an A0, but you might not have that. And in normal mathematics, A plus A, if it's not characteristic 2, A plus A won't be an A0. So here are some possibilities. You can take abelian groups. A0 is 0, that's the usual possibility. Supercoupled semi-ring will have A0 be A plus A. The hyperpair will be A0 being all sets, such that 0 is contained in the set. Exterior algebra, or exterior semi-algebra, will have V wedge W plus W wedge V is an A0. So you don't have a negation, so this is what A10 will be. Lie pair, again, you don't have a negation, so you have XX is an L0, XY plus 1X is L0, you have Jacobi identity, the reverse of the Jacobi identity, and then this kind of weak process. So this is good for matrix theory and linear algebra, because matrices over a pair are a pair. In order to have a robust theory, we need more assumptions. We need some subset, distinguished subset of A, which generates A additively, is disjoint from the null elements, contains 1, and you have a certain amount of distributivity. And then we'll call this admissible. And we'll only talk about admissible pairs. Now for polynomials, the point of all of this is that, I said matrices, also polynomials over a pair are again a pair. You just do the usual polynomial multiplication and addition. And the tangible elements, the T, will now be the monomials with coefficients in the original tangible elements. And so here, polynomials, the category of pairs permits polynomials, whereas hyperrings do not. Polynomials of hyperrings are not a hyperring. And you can take Lorentz series, Q polynomials, non-associative pairs, etc. Now, here's another example. You can have you can say that the sum of any two elements unequal is infinity, and then say that A plus A is infinity, or the other possibility is A plus A equals A. So this gives you two pairs which are difficult to categorize, to explain in other systems. And finally, our final property that we want is an element which acts like -1. In other words, 1 plus 1 dagger is an element which we'll call E, which is a null element. But 1 dagger might not be uniquely defined. In this example, it's not. But E is uniquely defined. And so we'll call AE A0. AE will be called A0. And then you have distributive and idempotent. Okay. So if A and A0 have property N, then this works. So this circle property is like a homomorphism, not quite. And if E distributes with the other elements, then E squared will be E plus E. Okay, so as I said before, A naught takes the place of 0. And property N replaces previous work on triples. Okay, so we're also going to ask for a kind of cancellation. If AB is an A naught or BA is an A naught, then B is an A naught for any tangible element of A. This will work when this is a group, for example, and also usual kind of cancellation and the kind of distributivity that okay. So our main pair is called a metatangible pair. That is that the set of two tangible elements is either tangible or no. And a special case of this is that the set of two tangible elements is one of them or is null. Now look at the similarity to valuations. See, if you have an ordered group, then A1 plus A2 would be the maximum or the minimum, depending how you define valuation. Or they have the same value. Okay. So now we need some way of comparing two tangible elements. So for the first kind, it's very simple because it's like characteristic 2. So you'll say that two elements are A balances A1 balance, B1 balances B2, if and only if B1 plus B2 is an A2. For the second kind, you need a more complicated definition. But the idea is that two tangible elements balance them if they're almost the same. Okay, so now what do we do for matrices? Well, you have a track and you define determinant to be the permanent in first kind. For the second kind, you need a more complicated approach. You have the even permutations, which give you the plus part of the derivative, plus part of the determinant, and the odd tracks, which give you the negative part. But you can't take the plus part minus the negative part because you don't have negation. So we'll say that a matrix is singular if and only if the plus part balances the negative part, according to the definition I gave on the last slide. And otherwise, A is non-singular. So this gives you a notion of a singularity of matrices. And the submatrix rank is the largest size of a non-singular square submatrix. Okay. On the other hand, you can define vector spaces in the obvious way and module the operations to component-wise. And we'll say that we have dependent vectors if and only if the sum of some linear combination is in the null vector part, A naught to the N. And the row rank is the maximum number of independents. The column rank is the maximum number of independent columns. And so this leads us to question, how do you compare these different ranks? And there are three conditions. One is that the submatrix rank is less than or equal to the row rank. Second is the subrank matrix rank is greater than or equal to the row rank. And there's a special case of this condition. Okay. So in order to be able to handle this, we have the concept of a modulus. And that's like evaluation. It's a semiring homomorphism to a bipotent semiring. Now, we will generalize this slightly, and I'm sorry, and say that a modulus on a pair is a homomorphism from A naught to a bipotent, to a minus bipotent, to an A naught bipotent semiring, or G naught, I guess you would call it bipotent semiring. So this is almost like evaluation. And condition A1 holds, and sometimes one gets, well, this is with joint work with Gobert and Akayan, that was lost in one of the early slides. And they got a version of Cramer's rule. Condition A2 is subtler because, in fact, there's a counterexample. If you take the semiring, sign semiring pair, where you have usual multiplication and addition, except that 1 plus minus 1 is infinity, then if you write plus for plus 1 and minus for minus 1, this has rank 3. These are not dependent, but every minor is singular. So, so that is a counterexample. The minors have rank less than 3. There's a 4 by 4, so this is a 4 by 3 example. There's a 4 by 4 example if you just add zeros and then plus at the end. But there's no 3 by 3 example. And so we have positive results for condition A2, but they're if they're like the supertropical algebra, you can generalize that slightly to and then you get condition A2 holding. Okay. So thank you very much, and it's an honor to be here.